Hi everybody, welcome back to Dave's Math Channel. This is my new feature on daily math problems, which I'm posting on a Facebook group I like to visit called Classical Mathematics. Try to post problems every day. I don't do it quite every day, but I do. I guess I posted a pop problem last night, which one of the members of the group solved, and um, I also solved it numerically. He solved it both numerically and analytically. Anyway, the this is a problem involving number strings. So let's begin. So first I have to state the problem. Here's the statement of the problem. So we're given a set of strings. So we're considering the set of strings that are whose elements are 0, 1, and 2, but we're not allowed to have two consecutive 2's. So if you like, these are strings of digits, but the digits can only be 0, 1, and 2. So it sort of looks like a ternary number, but it can start with a string of zeros, and it can never have two consecutive 2's, two or more consecutive 2's. So now the problem, and we're letting n sub n be the number of such strings of length n. Um, and so there's three parts of this problem. The first problem is just to compute n sub 3, the number of such strings of length 3. That's pretty straightforward. You can kind of list them all. But then the parts B and C are a lot harder. Part B, I'm asking for n sub 10, the number of such strings of length 10. That's very difficult to, write them all down. You might be able to do it with a computer, which is what I did. I used Mathematica to solve it. I'll show my solution in a minute. And then I think the hardest part of this problem is part C. And this is to find a general solution to this problem that works for all n. For every positive integer n, find the number of such sequences of length n. We're going to have to do an analytic solution to do that part. And that's probably the hardest part of this problem. But anyway, like I said, there's a numerical way to solve this problem, which I also call brute force. I mean, you can just kind of write computer code to, go through all the possibilities for strings of a given length. That's what I did here. And uh, yeah, so I'm just gonna kind of go through this code. So, um, so I mean, I don't know how many guys are familiar with computer programming. I actually worked at Wolfram Research where they were involved in making code for Mathematica, which is what I'm using here. Nowadays, it's called Wolfram Mathematica, but this is the latest version of Mathematica I'm using, and I have this function I call number strings, and you can write very similar code in C or C++ or pretty much any other programming language. I'm just going to go through this pretty quickly. So this is a loop. This is that actually involves a nested. It involves a for loop and then a couple for loops inside that for loop. So what I'm doing here is I'm looping. I'm letting m. I'm letting m be an integer that can go from 0 to 3 to the n minus 1. And the reason I'm doing that is because I'm going to consider ternary expansions of m. Those are kind of like decimal, but they only use the digits 0, 1, and 2. Ternary is just base 3. So you can sort of write out all the base 3 numbers from 0 to 3 to the n minus 1. If you append zeros to the left end, those are all going to have length n. But that doesn't quite do the job because you're going to get too many. You're going to get all the strings that have consecutive 2's, two or more consecutive 2's, but we want to eliminate those. And that's kind of what I do with the second for loop inside the first for loop. You notice that I have a condition here. If digits of I equals 2 and digits of I plus 1 equals 2, that's just another way of saying that there's two consecutive 2's. We don't allow that. So I say OK equals false. And if it's not okay, I don't append it to the list of results. That's all I'm doing. So I'm basically just listing all the results, using a ternary expansion and eliminating the ones that don't work. That's kind of what I'm doing here. So anyway, yeah. So that's the code, and it did work. I tried it, and here's the results I could obtain for n equals 1, 2, and 3. For n equals 1, it's kind of what you expect. You get 0, 1, and 2. You don't have to worry about in consecutive twos because these are just strings of length 1. For n equals 2, now you have 2 digits, and I wrote these digits spaced pretty far apart. I mean, I'm writing them out as strings, not as I mean, as lists in Mathematica, not as numbers. Um, but I think you can see that you get every possible string of length 2 except for 2, 2. 2, 2 is not included. It should be the pair on the bottom, but that one's not there, so you get a total of 8 rather than 9. And then for length 3, you'll notice there's several that are missing now. I mean, everything that would have involved 2 2s, and I think there's 5 such strings. I mean, 0, 2, 2, 1, 2, 2, 2, 2, 2, or 2, 2, 0, or 2, 2, 1. Those are the ones that are missing. So you'll get 22 strings of like 3, 27 minus 3. If you like, 27 minus 5. If you like 3 cubed minus 5. So that's nice. I mean, now I solved part A numerically using brute force. And since this code is very fast, I'm running this on a pretty fast computer. I can do this for strings up to length 10 pretty easily. This took less than a minute. So I just hear what I'm doing. I wrote another one line function here called length, en, and I didn't call it capital N because that name is reserved in Mathematica. I called it capital E, lowercase n. This is just a function that counts how many strings there are of length n, and this table lists all of them up to n equals 10. So this solves part B. I think you can see from this list the last element, the entry of this table is 24,960. So that's the number of strings of length 10. That would be very, very difficult to do by hand. So it's a good thing we have computers to do this. But we still didn't solve the problem in its full generality because, this is a brute force solution. This doesn't give you a general solution. I guess you could do it for as large n as you want if you wanted to wait long enough on your computer. But it's nice to have a general formula. Plus, it would allow you to compute them a lot more quickly if you did have such a formula. Well, it turns out you can do this as well. This is an analytic solution. And, one of my friends on Facebook, I forget his name, but he actually came up with this solution. Very clever solution. I did it too independently of him. I mean, but anyway, here's how I did it anyway. I think he did it very similarly. Um, but what you do here is let me just get to the slide here. Uh, Yeah. The way I did this was I introduced a couple other numbers here, L sub n and M sub n. L sub n is the number of sequences of length n that don't end in 2. In other words, that end in 0 or 1. And M sub n is the number that end in 2. So obviously n sub n is L sub n plus M sub n because either they end in 2 or they don't. But another thing you'll notice, L sub n is equal to 2 sub n minus 1. Why is that true? Because the number of sequences that end at 0, 1, every sequence that ends at 0, 1, you can get from an arbitrary string of length n minus 1 and add either a 0 or 1. So you just double the number of strings of length n minus 1 because you're adding either a 0 or 1 to the end. So you have two n sub n minus 1 strings of length n that end in 0 or 1. That's what I was calling L sub n. Therefore, L sub n is 2n sub n minus 1. But then what about M sub n? Well, M sub n is the strings that end in 2. And, the only caveat for that is that the string before it. If you're adding a 2, the string that you're adding it to can't end in 2. In other words, it has to end in 0, 1. Well, the number of such sequences is just L sub n minus 1. Therefore, M sub n is L sub n minus 1. So we have these three equations here. And now we can just do some algebraic manipulation, some substitution, and get a recurrence equation involving just capital N sub little n. So you write capital N sub n is L sub n plus M sub n, but L sub n we said was 2 sub n, 2n sub n minus 1, and M sub n was L sub n minus 1. We just do one more substitution. We get 2 capital N sub n minus 1 plus 2 capital N sub n minus 2. So we just derived a recurrence formula for the sequence capital N sub n. Here it is. Capital N sub n is 2 capital N sub n minus 1 plus 2 capital N sub n minus 2. Now, there's a well-known method for solving recurrences like this. The method involves, I'm not going to go through the whole method, but it turns out that you can write the general solution as of A times R sub plus to the nth power plus B times R sub minus the nth power, where R plus and R minus are the two roots to the quadratic equation R squared minus 2R minus 2 equals 0. And you get that from, you could write N sub n minus 2N sub n minus 1 minus 2N sub n minus 2 equals 0. The coefficients of that are 1 minus 2 and minus 2, and those are also the coefficients of your quadratic equation for this number R. You can just check that this is true. I mean, by plugging in the numbers, you can see that this works, because if you had N sub n was powers of R, then you would just see that this recurrence requires this equation to hold. And you can solve for the r's because this is a quadratic equation. We can just plug in the quadratic formula. When you do that, we have a equals 1, b equals minus 2, c equals minus 2. So you have, you probably remember the quadratic formula. You get minus b plus or minus square root of b squared minus 4ac over 2a. In this case, negative b is 2, and the discriminant b squared minus 4ac is 12, and then 2a is just 2, so you get 2 plus or minus square root of 12 over 2, which we can simplify to 1 plus or minus square root of 3. So therefore, the general solution to our recurrence is a times 1 plus square root of 3 to the nth power plus b times 1 minus square root of 3 to the nth power. We still don't know what a and b are. We still have to solve for them. But the way we do that is we plug in our initial conditions. So remember, it's easy to check. You can do this by hand very easily. You can check that n sub 1 is 3. The solutions of length 1 are just 0, 1, and 2. So there's 3 of them. So therefore, we have 3 equals a times 1 plus the square root of 3 plus b times 1 minus the square root of 3. That's just what you get when you plug in 1 for little n. And then when you plug in 2, there's 8 solutions. Remember, we had the 9. There's 9 strings of zeros, ones, and twos of length 2, but then we're not allowing 2. So that gives us 8. So now we just plug in again for n equals 2. We get 8 equals a times 1 plus 3 quantity squared plus b times 1 minus 3 quantity squared. Well, 1 plus or minus square root of 3 is just 2 times 2 plus squared. 1 plus or minus square root of 3 quantity squared is just 2 times 2 plus or minus square root of 3. You can check that yourself. So we get 2a times 2 plus square root of 3 plus 2b times 2 minus square root of 3. That's equal to 8. We can divide that equation by 2. And then we get 4 equals a times 2 plus square root of 3 plus b times 2 minus square root of 3. But then we also have another equation we just derived when we used n equals 1. That was 3 equals 8 times 1 plus square root of 3 plus b times 1 minus square root of 3. So this is a system of two simultaneous linear equations and two unknowns. And you can just do algebra to solve them. I'm not going to bore you with the details here, but what you find is that a is equal to minus b is equal to the fraction 3 plus 2 times the square root of 3 all over 6. So we just solve for a and b. And finally, we can plug in from our formula from before and get the final answer we want, a formula for capital N sub little n. And what we find is it's equal to this kind of ugly fraction. It's 3 plus 2 times the square root of 3 times the quantity in brackets, 1 plus square root of 3 to the nth power minus 1 minus 3 to the nth power all over 6. And this is always an integer. This is an exact formula. I mean, it's a little remarkable. This always gives you an integer, but this is a very nice way to calculate it on a computer, by the way. The term on the right, 1 minus square root of 3, that has absolute value less than 1. So when n gets very large, that term is going to go to 0. So you can just approximate this as 3 plus 2 times the square root of 3 times 1 plus square root of 3 all to the nth power over 6. And you can calculate this for very large n. I mean, you can calculate for n equals 100 or 1,000. I haven't done that, but you can try it yourself. Computers can do this very easily. So this is very nice because now we have a general formula for the number of such strings of any length you want. So anyway, that completes my solution of this problem. So thank you for watching. Long live math, and I'll see you guys next time. Bye.